Okay, 8 and 5, lesson 5, graphs of functions and equations. Again, a little bit of building blocks, a little bit of repeat knowledge. I will definitely get to the a few homework helper examples at the end. If the stuff is going too slow for you, or you're like, wow, I already remember all this, Mr. Lipscomb, just shoot down to the end and get the homework help. Make sure you can do that. Otherwise, just skip on over to 8 and 5, lesson 6. But yeah, the homework help, I think, is always something that is useful for almost anyone, just to verify that you know what it is we're talking about, what it is the lesson's about, and to verify that, and to just watch some of the homework get solved, or problems that are like the homework. So without further ado, let's scoot on over to our sketch pad. Mr. Lipscomb, slow down. You're talking too fast. Okay, so we'll slow down here. All right, so two things that we need to recall, and we're going to talk a little bit about these terms again. We've learned about them and spent whole lessons on them. But the idea of discrete versus not discrete functions, right? A discrete function is one. This will be discrete. A discrete function is one where you have kind of unique or distinct inputs, like your input is 1, 2, 3, and you get an output. And you don't have a well, let's draw the non-discrete. So non-discrete would be something more along the lines of a line like this. Now they can have the same description. You could have like y equals 2x be this and this. I mean, this could be the function that defines both of them, but on this side, let's say your domain, your inputs are restricted to integers. So your example question might be, candy bars cost $2 each. So here you can only buy, in whole increments. Over here, your domain can be anything. Your domain is or any positive. So let's do an any positive. And this would be like gas costs $2 per gallon. So on gas, you can buy 1 gallon or 2 gallons, but you can also buy 1.5 or 1.4 or 1.32169 or 0.0010024. You can buy any amount of gas. So this is a continuous function. And so because it's continuous and it's every single point is included, you can't circle any discrete points. Over here on the discrete function, I can circle individual points. But over here, I can't circle. Every time I draw a circle, I get a number of points. So this is not discrete, and this is discrete. And we covered that in the last lesson. And notice, this function here describes both graphs. It's just that in this case on the left, we're restricted to integers. On the case, whole numbers. On the case on the right, we're restricted to just positive real numbers. So that's discrete versus non-discrete. Now linear, so let's just undo all this. And then linear versus not linear is a different question. So in this case, we're talking about, this is basically, linear was all about 8M4. We spent so much of 8M4 talking about linear equations and how to solve them and how to graph them that I don't know that I need to really get into that. But a nonlinear Well, we'll just draw a quick one. Right, linear equations can be identified by a line or graphed as a line. This is a linear. Nonlinear is anything else. There's lots of nonlinear equations. You could have one that looks like this. This is nonlinear. You can have something that looks like this. That's not linear because I can't draw a line. I can't draw a straight line to connect all the points. So a nonlinear equation is any equation that cannot be graphed, that cannot graph a straight line. Now, a linear equation can also be discrete. So you could have a linear equation that looks like this. This is also linear. As long as I can draw a straight line through all the points. As long as I can draw a straight line through all the points, this is linear. Okay, so I'll review. Now, one last piece of review. It is not possible for two different points in the graph of a function to have the same x-coordinate. And this is going to be, there's some homework questions on this. So make sure you understand this. We have discussed this before. So let's look at this real quick. And sorry, I'm not drawing straight lines. I'm just kind of going quick and dirty here. But this is a function, or this could be a function. But if I draw this point here, this is not a function. And the reason is because in this one case, I have an x value of 1, 2, 3, 4, 5, and I have 2 y outputs. Okay. Similarly, this is not a function because I can find points here where I have an x input of 2, but I have 2 y values. Or even here, I have a point of x equals -2, and I have 2 y values. So these are kind of the two things that we're going to go over today. We're going to make sure that we understand this idea that functions cannot have 2 y values or even more with one x value. And then over here, we're going to look at some of these equations and just kind of go back and forth between graphing and the equation and the graphing equation, the verbal model, and the t-charts. So a lot of overview, actually. So let's look first. It was something, and we've spent a lot of time on this, but this is, again, you know, what they like to do in Eureka Math is kind of review and build and remind. So that this part of today's unit should sound really familiar to you. We're talking about a linear function. And so we have, and this is my example, but it's like one in the book. And we say, well, Kim runs 6 miles per hour. Well, this is remember, when we talk about linear functions or any functions, verbal model, algebraic equation. It could be algebra or an equation. And a chart, t-chart, and a graph are all the same thing. And we're going to extend it, and we're going to talk a little bit about whether this one's linear, nonlinear, discrete, or not discrete. But let's remind ourselves, Kim runs 6 miles every hour. So that means, after 6 miles per hour, let's look back at our code words. Miles per hour, this is our rate. Remember that keyword per tells us it's a rate. And we know that rates are slopes. And slopes in a linear equation, y equals mx plus b, the slope is the x coefficient. So we have our y equals 6x. Our B is our starting point. Well, if Kim's run 6 miles per hour and she starts, at her house, she hasn't gone anywhere. So that B is 0. So we just don't write it. So that's how we get from our verbal model to our equation. Now our equation to our chart, we just start filling in numbers. Well, if X is, our X is our input and our Y is our output. So if our X is 0, we get 0. If X is 1, Y is 6. If X is 2, Y is 12. Now notice, and then we can go about graphing that. 1, 6, 2, 12. Notice that my scale here is 0, 10, 20, 30, 0, 1, 2, 3, 4 in hours and miles, right? Our hours go on our x-axis. And as we learned, remember, time almost always goes on our x-axis. So this is our graph. Now, how far did Kim go somewhere in half an hour? Well, if she's running this distance, yeah, well, in half an hour, she went some distance. And that turns out to be 3. And she ran somewhere in 1.1, 1.2, 1.3. She didn't just magically appear an hour later, 6 miles down the road, or in 2 hours, 12 miles down the road. It was a nice, continuous, smooth run, which tells us that this is what kind of function? Discrete or not discrete? Yeah, you're right. It's not discrete because it's nice and continuous. We can take any input, any fractional or real number input that's greater than 0, and it's nice and smooth. Okay. Now, is it linear or nonlinear? Well, we know that this is linear. Why? It's linear for a number of reasons. 1, it's a straight line. And so we see that in the graph. And 2, the equation has no exponents in it. It does has the implied exponent of 1, which is what we want. So a linear equation can be written as y, y to the first equals 6x to the first. But we don't write these because they're 1s. Okay, so that's easy. We've done this. We did a whole unit on this. We spent probably 2 months on this. So this is very familiar. But what we want to do is we wanted to connect in this linear versus nonlinear and this discrete versus not discrete and say, well, this example, we need to characterize it as one or the other of linear, nonlinear, and one or the other of discrete or not discrete. Okay. Let's move on to another example, and I bet you can guess what kind of example this is going to be. This is going to be, and this is actually, I'm going to call this one homework help. And now the way that we're going to do this problem, because we don't know how to graph these. Now, if we know that this is not, we know, because we have an exponent, we know this is not linear. Right? We spent a lot of time in 8 and 4 saying, well, if we have exponents in our equations, we know these things are not linear. So, because it's not linear, we don't really know how to graph it. Because we know how to graph y equals mx plus b, but this is y equals mx squared. So we don't know how to graph it. So the only way we can graph this for now is to use a t-chart and then plot it on this graph here. So I want you to plot your turn. I want you to plot this data in a table. Then I want you to take the points that you get on this table and plot it in a graph. Then I want you to decide, is it a linear equation? And you know the answer is no, but I want you to see that it's not a straight line. I want you to tell me how far would this rock fall in 10 seconds? And here you can use the equation. Use the equation. And then for E and F, I want you to estimate using the graph how far would the rock fall in 3.5 seconds. Uh-oh, I've got a messed up, no, 4, 5, 6, 7. Okay, so how far would the rock fall in 3.5 seconds? And then I want you to look at the graph and tell me how long it would take it to go 500 seconds. So you're going to find something here, and you're going to find something, a point here. Okay, pause and try. All right, I assume you're back. Now let's go. So let's plot this data in a table. Well, if x is 0, my distance is 0. If x is 1, I get 16 times 1 squared. And right, we have to square the 1 first. We don't multiply by 16. Our order of operation says exponents before multiplying. So we get 16. And then we get 16 times 2 squared, and that equals 64. And then we get 16 times 3 squared, and that's 144. And now we get 16 times 4 squared, and I need to go to my calculator to do this one. Oh, why did I need to do that one? I knew that one, 256. And now 16 times 5 squared, I'm pretty sure that's 400. Yep, that's 400. 16 times 6 squared, and that's 576. And then 16 times 7 squared, and that's 784. So let's plot that data here on the table. I'm gonna erase this here. Let's plot it in a nice, pretty green. Okay, 0, 0, 1 comma 16, way down here. 2 comma 64, still way down here. 3 comma 144. And notice why I took, I made this be 800, because I knew that I had to fit 784 on here. So I had to use a scale where 800 was at the top. If I would have started going 10, 20, 30, I would have had 100 at the top, and I wouldn't been able to fit all these y values on. 4 comma 256 is right about here. Now you can see this. There's an interesting shape going on here. 5 comma 400. 6 comma 576. And then 7 comma 784. So notice what this shape does. It starts getting steeper, and I'm not a great artist. And this should be a pretty smooth line, but so there we have it. There are points, and there's our graph. Now it's not a perfectly, it's not a perfect graph, but again, graphs are pretty good are often good for estimating. Graphs are great to estimate and to visualize, because I can immediately see, this isn't linear. So I say this is not a linear equation, because it's not a straight line. The points do not line up. Okay, and I knew that, again, because I had an exponent here, but good that we can see it visually. So how far would this rock fall in 10 seconds? And I said to use the equation. So let's use the equation and go, well, y equals 16 times 10 squared. That would be 16 times 100. That'd be 1,600 feet. All right, 16 times 10 squared, 1,600 feet. Now, by looking at the graph, let's see, how far would a rock fall in 3.5 seconds? So in 3.5 seconds, let's make an estimate. It looks like maybe about 200 feet, huh? So let's just put down that that guess here, and let's see what happens. Let's guess 200 feet. And so I'm going to plug that into my calculator and see how close it is to the actual answer. 16 times 3.5 squared. Oh, look, the actual answer is 196. This is the actual answer. So 200 feet, pretty good estimate. Our curve is looking like it's representing some good numbers. Now, let's see, by looking at the graph, how long would it take the rock to fall about 500 feet? So here, let's look at 500 feet. And let's say, well, maybe about 5.6 seconds. And let's see, how far would a rock actually fall in 5.6 seconds? 5.6 seconds, it would go, oh, wow, that's pretty good. It would go about 501 feet. So these are both great estimates. 200 feet in 3.5 seconds and 5.6 seconds to go 500 feet. So this graph did a great job. Now you have a good, this is like some of the homework help or some of the homework problems that you're going to be solving, and a lot of the similar questions that it's going to be asking. So good luck on the homework there, and then we're going to go into this last little piece of homework help where we talk about functions, and this should be hopefully pretty easy. So the question is which could be functions? Well, let's look at this. Remember, we're looking at the each input can only have one output. So let's look at this first one. So you can pause and try. I encourage you to pause plus think. I had this new step in, think. Pause plus think plus try. And I'll label them, 1, 2, 3, and 4. Okay. I assume you've paused and tried, so let's look. We have a problem here, Houston. Right here, we have one input, we have two outputs, and for the negative 1.5, if this is negative 1.5, we have two values, or two outputs for one input right here. How about here? Well, this is a function. This could be a function because for each x, there's only one output. And how about this one? This one is also a function. There's no place where I can take a circle and see two outputs for one input. So this is a function. And then here, this is not a function. And the reason is because there's a number of places here, not. There's a number of places here, like right here at 1, where I have two outputs. Right here I have two outputs. So everywhere right at 0, I have two outputs. So this is not a function. Another way to look at this, I'm just going to do this really quick. I wasn't planning on this, but let's look at this thing. It's called the vertical line test. This is something that some teachers teach, and so I'm just going to show it to you real fast. I've talked about it before, the vertical line test. So a functions must pass this test. And the test is, if I draw a vertical line, I will only touch the output. I will only touch 1 or 0 points. I will never touch 2 or more. That's the vertical line test. So here, if I can draw a vertical line on number 1, I can draw a vertical line right here. Let me actually just use the line. Why not use a line, Mr. Lipscomb? So I can draw a vertical line and I can hit 2 points. So this is not. Here, there's nowhere I can draw a vertical line and hit 2 points. Here, there's nowhere I can draw a vertical line, and hit 2 points. But here, I can draw a vertical line and I can hit 2 points here. I can do it here. I can do it here. So, in other words, this fails. This one, these ones fail. So these are not functions. And these ones are okay. And you know what? I have not laid down a happy cat yet. So I just want to lay down a happy cat because, you know, happy cat, happy math. I love teaching math and I love my happy cats, and they just kind of remind me that math can be fun and I don't always have to be so serious. Okay, and that's it. I'm done. This is it. 8 and 5, lesson 5. We can call this one good, and I'll move on to 8 and 5, lesson 6 tomorrow, and we'll be talking to you. We'll be talking to you soon. You're welcome.